Hi, I'm Graham Lewis, and in this problem we're going to look at a normal distribution problem where we actually are given the areas and we have to calculate the z-scores, so go backwards. And then once we've got the z-scores, then we can solve the problem to estimate a mean and standard deviation of this problem. So we have the masses of boxes of oranges are normally distributed, so 30% are greater than 4 kilograms and 20% are greater than 4.53. So with that, we can find an estimate for the mean and standard deviation of the boxes. As before, always define your variable. So I'm going to let W be the weight in kilograms of one of the orange boxes. Then draw pictures. Now I've got two bits of information. I know that 30% are greater than 4 kilograms. 30% are greater than 4 kilograms. So is 4 kilograms, think about it, left of the mean or right of the mean? Well, because it's 30%, it must be right of the mean here. Because obviously if it was left of the mean, it would be bigger than 30%, say 80% or 90%. So this is 30%, which is 0.3 this area, and that matches a weight of 4 kilograms. Equally here, this must be 4.53 kilograms, and this area here must be 20% or 0.2. Okay, so now I'm going to show you using tables how to work out the z-scores. Now, if you remember, the z-score tables and your calculator work from going from minus infinity up to a value. So I can't look up 30% either from tables or my calculator. I have to actually work out what I don't want, which is 70%. So in the tables, or if you're using a TI, Texas Instruments calculator, then you're going to have to input 70%. So I'm interested in the area going from minus infinity up to a certain z-score gives me an area of 70%. Let's have a look at the tables. Now in AP Statistics, I'm just looking for the area that is closest to 70%. Remember, these are the z-scores in the columns and row titles, and the black numbers in the middle are the probabilities, the areas. So I'm trying to find an area as close as possible to 70%, 0.7. You can see we've got two possibilities here. We've got 0.6985, which is 0.0015 away, and 0.7019, which is 0.0019 away. So actually, this one here, 0.6985, is slightly closer, so that's the one I'm going to take. At AP, it's fine that it's not perfectly on. If you're doing another course, you may do, if you're using tables, do interpolation, but not in AP Statistics. Of course, your TI calculator or another calculator will give you a much more precise number, but this is good enough. So the z-score is 0.52, looking at the tables there. So we've got z-score of 0.52, just looking at 0.5, and then add the 0.02. Okay, let's go back to our problem. So I've drawn a picture, I've written down the corresponding z-score, 0.52, and notice I've made it really clear for the person that's looking at my work where I got that. From tables, the probability of z is less than 0.52, is 0.6985. So they're in no doubt that I know what I'm doing, and you've clearly stated what you're doing. Let's find the other z-score now, because now we know that 20% of oranges, boxes of oranges, are above 4.53. So we know that. Let's draw another picture. 20% here are above 4.53. So in my tables, or using the calculator, we need an area of 0.8. So maybe we'll show you the calculator version now, but I have the TI-83. Okay, so I've entered on my calculator by pressing second function vars to get me to the distribution, choosing the third option, which is inv norm. I enter 0.8, that means the area I don't want, because remember it calculates everything from minus infinity up to that point, so that's my probability on my area. I've entered the mean, the population mean, and I've entered the standard deviation, or those people that think of that, because obviously the standard deviation there is the same as the variance, it's 1. And then the calculator outputs a number which is much more accurate than tables, 0.841621, etc. Okay, so that is our second z-score. However, I wouldn't personally leave it like that because I don't think that's good statistics, because that's a calculator printout. I would actually like to write down what I'm doing there. I would write that down. so the person marking my work knows that I've used my calculator, but then I would write that because I think it's nice to show it in non-calculator output to show your statistics properly. So we know that the z-score is actually 0.841621, so that's my z-score, and we know that the area is 0.8. So in other words, I know that probability of my z-score being smaller than 0.841621 is equal to an area of 0.8, and I'm writing down from my TI 83 plus. So the person marking my work knows perfectly well that I understand what I'm doing. So that's what I would write down. I would also include this here, just so that they're really clear what I have done. Okay, so now we've got our two z-scores for our corresponding areas, we can solve the problem to find out the mean and standard deviation. And this is a little bit tricky, and I'm going to show you two ways of doing it. I prefer the second way, but I'll do probably what's considered more straightforward the first way. So method one is I've drawn a picture there, and we know that a weight of 4 kilograms corresponds to a z-score of 0.52. I've rounded to 2 decimal places, that's fine, you're allowed to do that with z-scores. If you want to keep more accuracy, you may. And 4.53 kilograms matches to a z-score of 0.84. So we know for both of those z-scores, my two z-scores, z1 and z2, that we can use the formula that z1 is x minus mu over sigma, and also z2 is x minus mu over sigma. So if we just do this quickly, we know that 0.52 is 4 minus mu over sigma. And I also know that 0.84 is 4.53 minus mu over sigma. And hence now we can solve this pair of simultaneous equations. So if I multiply both sides by sigma, I get 0.52 sigma equals 4 minus mu, and if I multiply, and I'll call that equation 1, and if I multiply this by sigma, I get 0.84 sigma equals 4.53 minus mu, and I'll call that equation 2. Now if I do equation 2 minus equation 1, so sorry, not 2 dash, equation 2 minus equation 1, I will get 0.84 sigma minus 0.52 sigma equals 4.53 minus 4, 4.53 minus 4, and minus mu minus mu cancel out beautifully. And hence I can work out sigma. So I'll just calculate sigma quickly. So subtracting the two equations give me a sigma value, an estimate for the standard deviation of 1.65625. I won't approximate that yet, round it yet. Let's sub it back into, I think, either equation, 1 or 2, which looks easier to you. I think 1 looks easier. So I'm going to sub it back into 1. So I'm going to sub it back into 0.52 sigma equals 4 minus mu. We know we're going to sub that back in, and solving that gives me an estimate for mu, which is 3.13875. And then I'm going to round at the end because I rounded my z-scores to 2 decimal places. So I'll do the same with my estimate for mu and sigma. So an estimate for mu and sigma are mu is 3.14 kilograms and sigma is 1.66 kilograms. Now I'm going to show you a different way of thinking about it, which conceptually I actually prefer and I think is simpler algebraically. Okay, so we know that a weight of 4 kilograms corresponds to a z-score of 0.52, and a weight of 4.53 kilograms corresponds to a weight of 0.84. And this way avoids simultaneous equations. We know that the number of standard deviations between 0.52 and 0.84 is the same number of standard deviations between 4 kilograms and 4.53 kilograms. The beautiful thing is that we know that the standard deviation for this distribution is 1, and the standard deviation for this distribution is the one we're trying to find out. But we know the number of those standard deviations is the same as the number of the standard deviations between 0.52 and 0.84. So therefore, it's simply a ratio 0.84 minus 0.52 times the standard deviation that we're trying to work out has to equal 4.53 minus 4. And solving that will give me the same answer I got before of sigma, which was 1.66 kilograms. There. So that is conceptually much easier, and then you can substitute sigma into either of the two equations to get mu. So this is the way I prefer. Hope you enjoyed this video and you used the method that you prefer. The important thing is showing you working well, drawing pictures, specifying the variables. Thank you very much. Have a great day.